Hello and welcome to Lesson 5 of Computer Systems for National 5 Computing Science. Last time we looked at ASCII, today we're going to look at graphics. We're going to cover most of this and we'll go into a bit more detail in the next video, but today we're looking at graphics. So in this presentation we're going to look at how graphics are represented in a computer system. And by the end of the lesson you'll be able to describe bitmaps, vectors, and you'll explain the benefits of each type. But first, there was a question at the end of the last video, and here it is. Each of the letters of the message FULL will be stored as an ASCII character. Calculate the number of bits required to store the message. Well, there are 4 characters, and if you remember from the last video, ASCII uses 8 bits per character. So what's 8 times 4? Let's get a calculator. 8 times 4 is 32. Look at that, fantastic. So the answer to this question is 32 bits. Well done if you got it right. So let's talk about bitmapped graphics. Bitmapped graphics are stored as individual pixels. If you don't know what a pixel is, if you look really close, I don't recommend this, but if you did look really close at the monitor, or if you used a magnifying glass, you would see these tiny little squares. They are the pixels. The smallest square that you have on your computer monitor, that is a pixel. The term pixel, look here, P-I-X-E-L, it stands for picture element. I don't know why X. Why is it not a P-I-C-E-L? I don't know. Picture element. In a bitmap, each pixel is stored, and each pixel has a binary representation. Here's a couple of examples. So in this example, here we've got the letter A. If we were to break it down into its individual pixels, it would look like this, kinda. And all the black pixels here would be stored as a 1, a binary digit 1. And all the white pixels that are around this would be stored as a 0. All the pixels in a bitmapped graphic are stored, and it's stored in a kind of grid. You can see it down at the bottom here. We've got this, I don't know what this is meant to be, like a Space Invaders spaceship maybe, something like that. And you can see that we have the graphic here, and you can see that all the white pixels are 0s, and all the black pixels are 1s, and we store every single pixel, regardless of how many colours you've got or which colours you've got. It's all being stored. And you might be thinking, well, that's pretty rubbish, but look at this, that's a rally car, can you see it? This isn't a great picture because it has 2 problems. It's purely black and white, and it's quite low resolution, to be honest. But bitmaps are used for photographic style pictures, so let's learn a little bit more about them. If you have a black and white bitmapped graphic, each pixel can be represented using a single bit. 1 for black, 0 for white. Whether it's black or white, you need 1 bit. But black and white pictures can be boring. We need more bits to represent colour. Now here's a bit of maths that you don't really need to know, but it's interesting. If you wanted 4 colours, you would need 2 bits. If you wanted 8 colours, you would need 3 bits. And up to 16 colours, you'd need 4 bits and so on. And you may recognise a pattern there. The number 2 to the power of the number of bits is how many colours you can represent. So if you've got 2 bits, you've got 4 colours. If you've got 3 bits, you've got 8. If you've got 4, you've got 16. And you'll recognise these numbers as well, 4, 8, 16. These are the binary values, 1, 2, 4, 8, 16, 32, 64, so on and so forth. And here's something that's going to really show you the power of colour. All the images that I'm about to show you have the same resolution. That means they have the same number of bits, or number of pixels rather, across the way, and the same number of pixels down the way. So it's the same resolution. We're not getting any more pixels in the following images. So as you can see, black and white is pretty rubbish. We've doubled the number of colours. So instead of black and white, we've now got black, white, purple, and green. And it already looks a lot better. 16 colours looking a lot better. Those droplets are starting to look really good. The leaves still look a bit rubbish though. Or if we had 8 bits per pixel, 256 colours, it's starting to look like an actual photograph. There is still a bit of, I don't know, like pixelatedness in the background here. But overall, this picture looks pretty decent. So you can see that having more colours is good. But the downside is they take up more bits per pixel. Now, you don't need to know this strictly speaking, so let's move on to more essential stuff. The other type of graphic, so bitmap is one type of graphic. The other type is called vector graphics. And these don't store every single pixel in the graphic. What they do instead is they store the mathematical representation of shapes and lines. For example, you can see the square down at the bottom right here. Instead of storing every single pixel in this shape, what we would store is the top left corner of it, the size of the sides, and we would store the colour that it's been filled with and the outline colour. these types of things. So the computer has to remember far less stuff. That'd be like a few bytes for the corner, a couple of bytes for the size, a couple of bytes for the colors, and there you go. Instead of a byte for every single pixel. Now this picture probably has a few hundred pixels across, a few hundred down. So that's going to be thousands and thousands of bytes. This image, now I know this this image is way less detailed than this one, but you can get the idea that this just takes up a few bytes. This leaf takes up a few thousand bytes. This will be demonstrated in a couple of slides though. Now you're probably immediately thinking that bitmaps are just better pictures. They're better for photorealistic images. It is possible to get really good looking images with vectors, but they are best suited to logos or cartoony graphics. One downside to bitmaps though is that when you zoom right in, now these images are pretty poor anyway, but when you zoom in or scale up a bitmap, you can see these jagged edges. It's like the pixelated sort of images. These are the actual pixels that you're zooming into. When you zoom into a vector, because it's been mathematically generated, I suppose, when you zoom in, it just calculates the shape again. It just recalculates it, draws it again, renders it on the screen, and it's just as smooth as it was when it was zoomed out. You can see a better example down here. We've got the original sized shapes. We've got the sort of male toilet sign here. And when you zoom in with a bitmap, it gets a bit blurry or pixelated. With a vector, it just recalculates the shapes, it redraws them, and it's perfect. Now, when I was talking about the storage required for bitmaps versus vectors, this is a better example. Look at the picture down below. So we've got this sort of screen size. Imagine this is a 1920 by 1080 image. So it's 1920 pixels across, 1080 pixels down. It's got a white background, and we've got this sort of peachy cream square in the middle. If we saved this as a bitmap image, we have to remember every single pixel in this image. All these lines of white pixels, we have to remember every single one. Hundreds of them, probably about 500 down to here. And then we've got more white lines, and then we've got some black pixels, and then some cream pixels, and lots of cream pixels, and then probably another couple of hundred lines of white pixels. We have to remember all of that in a bitmap. When it comes to a vector, you would store the background color, so white. There we go, that might take up to maybe 3 bytes, 24 bits total. And then we store the X and Y coordinate of the top left corner of this shape. So that's going to be another couple of bytes. And then the outline color and the fill color, that's going to be another 6 bytes in total. And you can see that we've stored 3 bytes for background plus a couple for that, it's 5, and then 3 more for each. Oh, and I forgot the side. The size of the sides could be another byte. So we're talking 12 bytes in total. 12 bytes, that's 96 bits. If this was a bitmap image, the calculation would be 1920 times 1080 times 24 bits for the colors. This is how many bits it would take up. 49 million. You can see that vectors definitely have an advantage when it comes to shapes. 96 bits to store this as a vector, over 40 million bits to store it as a bitmap. Right, so you've learned a little bit about bitmaps and vectors. Let's look at some past paper questions. Now in this first part of the question, it's obviously referring to a graphic that is further up the page. The user interface design is implemented. It contains a bitmapped graphic and some text, or maybe there's more context above. But you don't need to know the context in this case. Describe how a bitmapped graphic would be stored. What do you think you would say? Well, unfortunately, I don't have the marking scheme because the SQA have taken them all down from their website. But I remember this question, and you would say it's stored as a grid of pixels where every pixel has a binary number to represent its color. So a bitmapped graphic is stored as a grid of pixels where each pixel has a binary value to represent its color. 2 marks. We've got some reminder questions here. Let's see if you can do this one. State a standard code used to represent text characters and the number of bits used to store each character. I bet you can't remember the code. I'll give you a clue. The short name for it is ASCII, A-S-C-I-I. Okay, it's American Standard Code for Information Interchange. You actually would get the mark for just writing ASCII, A-S-C-I-I. But how many bits does it require? This was in the recap question on the very first slide or second slide of this presentation. 8 bits per character. That's the number of bits used to store each character. There you go. Right, I hope you've enjoyed this one. I'll see you in the next one.